We're going to have a look at 4 questions on worksheet number 22 here. Questions 6, 10, 11, and 15. Starting with question number 6, it says, calculate the force of gravity acting on a 5,000 kilogram satellite, whatever this satellite is, orbiting around the Earth at an altitude of 1.0 times 10 to the 6 meters above the surface of the Earth. Now, this is a pretty important part of this question, above the surface of the Earth. When we find the force of gravity given by Newton's law of universal gravitation, we want the distance between center and center, between the center of the Earth and the center of the satellite. Now, we don't have to worry too much about the radius of the satellite because it's going to be so small compared to this distance involved here. It's not really a big deal. But the radius of the Earth, that's going to be important. Here's the satellite way up here. Okay, here's the Earth right here. This is our distance above the surface, but we also need to include the radius of the Earth so that we have the distance from the satellite to the center of the Earth. We know the radius of the Earth. That's given to us on our data sheet. The radius of the Earth is 6.38 times 10 to the 6 meters. If we want to find the actual R value here from the center of the Earth to the center of this satellite, then we're going to add 1.0 times 10 to the 6 plus 6.38 times 10 to the 6 meters. That's going to give us 7.38 times 10 to the 6 meters. That's the value of R that we want right there. 7.38 times 10 to the 6 meters. Now, we know what M1 is. It's 5,000 kilograms. We know what M2 is. This is the mass of the Earth, also given to us on our data sheet. 5.97 times 10 to the 24 kilograms. 5.97 times 10 to the 24 kilograms. By the way, did anybody get those backwards and say M1 is 5.97 and M2 is 5,000? Is it a big deal? What's 1 times 2? What's 2 times 1? Doesn't matter what order we multiply those in, right? We get the same answer. So if we go M1, M2, or effectively M2, M1, it doesn't really matter. It's the same thing. So we're going to say F is equal to G M1, M2 over R squared. This is the force of gravity given by Newton's law of universal gravitation. By the way, some of you might be saying, well, why can't we just say M times G? Like, why can't we just say the mass of the satellite times 9.81? What's the problem with that? Well, this equation is actually valid. It is actually valid. The only problem is that when you're talking about 1 times 10 to the 6 meters above the surface of the Earth, you don't know what G is. G is not 9.81 anymore. G is weaker than that. If you knew what little g was, then you could say 5,000 times little g, whatever that is. But you don't. Does that make sense? On the surface of the Earth, we don't have to go through this process usually because we know that little g is about 9.81 meters per second squared. But if we're a large distance above the surface of the Earth, we don't know that. We don't know that it's 9.81. So we either have to find a little g or we have to use this bigger equation to find the force of gravity. G is 6.67 times 10 to the negative 11. That's the constant. M1 is 5,000 kilograms, and M2 was 5.97 times 10 to the 24 kilograms. We divide that by R squared, which is 1.0 times 10 to the 6 squared. Let's do this on a calculator to make sure that we can do it correctly. Let's say 6.67 times 10 to the negative 11. We're going to multiply that by 5,000. Multiply that by 5.97 times 10 to the 24. Then let's divide that. Let's use some brackets on the bottom. Yep. Oh, sorry, you're right. The radius is not right. We highlighted that even, right? The radius is 7.38 times 10 to the 6. Thank you. The good news is the calculations that I've done so far on my calculator, I haven't got that far yet, so I don't have to change anything. We're going to use the brackets on the bottom, 7.38 times 10 to the 6, and the bracket, and then let's just square that. We should get a value here of 3.7 to 2 digits, 3.7 times 10 to the 4 newtons. And we do use 2 digits because you can see here This one is 2 digits. Is that okay, everyone? So make sure that you're using the distance from center to center. We don't know the radius of the satellite, but because it's so small, it doesn't really matter. The radius of the Earth is big enough that clearly it matters. If you're ever given a question on a test and you're not sure what distance you're given, like let's say I give you the Earth-Moon distance, and you're like, oh man, I don't know, does that include the radius of the Earth and the radius of the Moon? Ask me, I'll tell you. Okay, I'm not going to tell you if you have to add a number to another number. I won't tell you that. But if you're not sure if a number already includes the radius or not, ask me and I'll tell you that. All right? You have to know whether you need to include it or not, but if you're not sure whether the number that you already have does include it, then you can certainly ask that question. All right, number 10. So a 30-gram mass is separated by a second mass by 30 centimeters. I want to convert grams and centimeters to meters. The force of gravity acting is 4.00 times 10 to the negative 13. That should be newtons, right, not kilograms. Determine the value of the second mass here. So let's write down what we have here. We've got mass 1, let's say, of 30 grams, which we're going to convert to kilograms by dividing by 1,000, 0.030 kilograms. They're separated by 30 centimeters or 0.30 meters. Reality is here, the distance from the center to the center, like, we have to add the radius of the mass in. No, like the number that I'm giving you here, we'll say that includes the radius of the objects, but the radius of the object would be so small that it probably wouldn't matter anyways. We have the force of gravity here is 4.00 times 10 to the negative 13. It should be newtons. And we want to find the value of m2. So here's our equation. Now, let's solve for the value of m2. What do you want to get rid of first here? There's a couple of options. There's not really one correct answer to this. Solving for m2, we got to get rid of g, we got to get rid of m1, we got to get rid of r squared. I'm going to get rid of the r squared first, although it doesn't really matter. We're going to do that by multiplying. We're dividing by r squared, so let's multiply by r squared to get rid of it. Now let's get rid of the g and the m1 together. You could get rid of them separately. I'm going to choose to get rid of them together. I'm going to do that by dividing. So m2 becomes equal to f times r squared over g times m1. Let's sub our numbers in here now for this. 4 times 10 to the negative 13 times 0.30 squared over 6.67 times 10 to the negative 11 times 0.03 kilograms. Okay, we certainly want to do this one on our calculator. Watch carefully how I do this correctly. Okay, I'm going to do it wrong first. Okay, and I want you to tell me where I've done it wrong. So don't enter it this way in your calculator because there's going to be a mistake here, okay? Tell me where the mistake is. Say 4 times 10 to the negative 13 times 0.3 squared divided by 6.67 times 10 to the negative 11 times 0.03. Okay, that's the wrong answer. Josh, where have I made my mistake here? Yeah, I got to put brackets on the bottom, right? I could do it on the top as well, but I don't need the brackets on the top unless there's an addition or subtraction in there. But on the bottom, I definitely do. So let's redo this now the right way. We're going to say 4 times 10 to the negative 13 times 0.3 squared divided by brackets on the bottom, 6.67 times 10 to the negative 11 times 0.03. We do this, and we get 0.017 or 1.8 times 10 to the negative 2 kilograms. How many people got that? Okay, good. Next question that we wanted to do here is number 11. Oh, this is a good one. I don't know how many of you would have gotten this one. There wasn't one that was quite like this on your example, so you had to really think about this one. It says 2 identical masses experience gravitational force. Attraction of 2 newtons are separated by a distance of 100 meters. What's the value of each mass? Well, first of all, you want to find 2 different masses, but they're the same value. So if you can find one, you've got the other, right? What's the value of M1? I don't know. What's the value of M2? I don't know. But if they're the same masses, why don't we just call it M? Instead of calling it two separate things, M1 and M2, why don't we just call it M? We have the force of gravity that acts between them. It's 2.00 newtons. And we have the radius, or the distance, is 100 meters. Let's write down our equation. Okay, we might not be sure how we're going to solve this yet, but we can at least write down the equation. F is equal to G times M1 times M2 over R squared. But what's M1 and M2? Well, they're the same thing, so let's call it just M and M. G times M over R squared. Wait a sec, what's M times M? M squared, not 2M. Okay, M plus M is 2M. M times M is M squared. So we've got F is equal to G times M squared over R squared. Now we're solving for M here. Let's take the R squared up by multiplying. F times R squared is equal to G times M squared. Let's take the G over by dividing. And then we want to square root that, right? Let's say M is equal to the square root of F times R over G. So we're going to say the force here is 2 newtons. R is 100 over 6.67 times 10 to the negative 11. I'm going to make a mistake on this one as well when I enter it into the calculator. Okay, watch for it. See if you can pick it up here. Yep. Have I? Did I forget? Oh, I did forget to square R. Yeah, thank you. So watch for the mistake here, okay? I'm going to say square root. I'm going to use some brackets here, right? Because doing something in square root, you want to use brackets here. Let's say 2 newtons, 2 times 100 squared, divided by 6.67 times 10 to the negative 11 bracket. Press enter, I get the wrong answer here. What's wrong with it? Yep. Yeah, let's use the EE button for that. Yeah, exactly. Now you could use brackets on the bottom there, but I would prefer you do this. Square root of 2 times 100 squared divided by 6.67 EE negative 11. So that ties the scientific notation with the base, the 6.67, whereas when I do it the first way there, it considers it a multiplication. When I do that, I get same base, 1.73, but this time it's 1.73 times 10 to the 7, not times 10 to the negative 4. Should be positive 7, I guess, kilograms. Is that good? Does it make sense how we entered that to make it correct? You don't want to like do all this correct and write it down correct and punch it into your calculator and get a wrong answer just because you punched it in wrong, right? Okay, last question we want to go over is number 15. How far above the Earth's surface does this mass experience a force of gravity at 8.68 times 10 to the 5 newtons? So we're going to say M1 is 1.00 times 10 to the 5 kilograms. We're going to say M2, this is the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. Sometimes, in some places you see 5.97, and in some places you see 5.98. I always forget on your data sheet, what does it say, 5.97? Yes, 5.97. Okay. The force of gravity here is 8.68 times 10 to the 5 newtons. And we're looking for R here, right? So we're going to say F is equal to G M1 M2 over R squared. Let's take the R squared up by multiplying. F times R squared equals G times M1 times M2. Take the F down by dividing. G times M1 times M2 over F. And then finally, let's square root that. R is equal to the square root of G M1 M2 over F. Good? So far, so good? All right, let's sub our numbers in here now. We got 6.67 times 10 to the negative 11 times the mass, 1, which is 1 times 10 to the 5 times the mass of the Earth. Divide that by the force. It's a pretty big force because we're dealing with the Earth here. And then we square root that. Let's do that on the calculator as well. I get the square root, bracket 6.67 times 10 to the negative 11 times 1 times 10 to the 5 times 5.97 times 10 to the 24. Divide that by 8.65 EE 5. And that should give me, never mind, I say it should give me my answer. Invalid dim. I don't even know what a dim is. Oh, what did I do there? 1 times 10 to the 5. Is that right there now? No. Okay, 6.67 times 10 to the minus 11 times 1 times 10 to the 5 times 5.97 times 10 to the 24. Is that right now? I think it is. Yeah, I don't have a dim now. I don't have a dim or valid or invalid now. Is that my answer? 6.78 times 10 to the whatever? 6784877. Is that right? Oh, don't tell me I made a mistake again. What did I say? Oh, man, 8.65, 8.68. Yeah, they're close enough, aren't they? No, they're not. Okay, let's try this one last time. 6.67 square root of 6.67 times 10 to the minus 11, maybe this time I'll get this right, times 1 times 10 to the 5 times 5.97 times 10 to the 24 divided by 8.68 times 10 to the 5. Oh, I almost did it again. Six, 7, 3, 1, 4, 2. .611. There's my answer, right? What have I just found? What have I just calculated? The value of r, right? But we're not looking for the value of r. We're looking for the distance above the Earth's surface. We found the distance from the center of the Earth to this object. We want the distance above the surface of the Earth to this object. So what are we going to do? Enrique? No? Yeah, subtract the Earth's radius. So let's say my answer here is 6773142.611 minus the Earth's radius. And when we do that, we get 4.00 times 10 to the 5 meters above the surface of the Earth. Now let's take a look at worksheet number 23. We had 4 questions that you were asked to do on that one, 1, 2, 3, and 5. We're going to do all 3 of those questions, 1, 2, 3, and 5. Starting with number 1, it says find the net force of gravity acting on object 1. Now, pay really close attention to this next step, because this is the important part, the most important part, the hardest part. Once you get past this, you're probably going to be okay. Draw the free body diagram. That doesn't sound very hard, but people get messed up on these free body diagrams all the time. You're drawing the net force on object number 1. Forget about object number 3. Pretend it doesn't even exist, okay, for now. You're finding the force of 2 on 1. 2 and 1 are going to attract each other by gravity, right? There's a force of attraction. If they're going to attract each other, then 1 is pulled towards 2. I'm going to say the force of 2 on 1 is to the right. 1 is pulled towards 2. Now, 2 is pulled towards number 1, right? By an equal and opposite force. But I don't really care about that because I'm not trying to find the force on number 2. I'm trying to find the force on number 1. So which way is the force of 2 on 1? It's to the right. Now, let's pretend 2 doesn't exist. Let's put 3 back. 1 and 3, do they attract each other? Yes, they do. 1 is attracted towards number 3. So I'm going to say that's the force of 3 on 1 to the right. 1 is pulled towards number 3. Now, 3 is also pulled towards number 1. Agree? But I don't really care about that one in this question because I'm not trying to find the force on number 3. I've got 2 forces, both to the right. Now, I can find the values of both of those forces using Coulomb's law. K Q1 Q2 over R squared. That value works out to, by the way, to be 1.25 times 10 to the negative 8 newtons. Now, F31 is K Q1 Q3 over R squared. That value works out to be 2.37 times 10 to the negative 9 newtons. What do you got to watch out for this? What do you got to watch out for here? Square it, yes, somebody said square it, absolutely. That's a common mistake, actually, forgetting to square that, especially since we've just finished talking about Coulomb's law, centripetal force. F is equal to mv squared over r. Sometimes we forget to square the r on this one, right? That's one common mistake. What's the other thing we got to watch out for, the value of r here? What's this value of r right here? Distance between 1 and 2 is 2.0 meters, right? What's the value of r right here? 3.75 meters. We need the distance between 1 and 3 to find the force of 3 on 1. So here's F21, here's F31. Now when I'm finding the net force, we do what we've done a million times before already in our last unit. F net is equal to the sum of the forces. We're going to say F21 plus F31. We add those up, both positive because they're both to the right. But you can see why we draw our free body diagram. Sometimes we're going to get a force to the left, and we have to pay attention to positives and negatives. Okay, we do this. It gives me 1.5 to 2 digits, 1.5 times 10 to the negative 8 newtons. I kind of skipped a little bit of work up here, right? You guys okay with what we've done there? I just skipped that because we went through a few questions on the previous worksheet with that, but if you need me to show more work, then we can certainly do that. You guys okay with both of these forces acting to the right? Yeah? Okay, that's critical here, right? Because if you get one of them acting to the left, then when you go to add them up, you're going to make one of them a negative value, and then that's going to give you the wrong answer. So as much as you do everything else correct, the calculations and so on correct, if you get your diagram wrong, then you're going to get a wrong answer. Okay, let's have a look at number 2. 2 says, find the net force of gravity acting on object number 2. Let's redraw this here. We've got We've got object 1, we've got object 2, and we've got object 3. We want to find the force on object 2. Let's pretend 3 doesn't exist. 3 is not there. We want to find the force on number 2. 1 and 2, do they attract each other? Yes, all objects with mass attract each other. That means 2 will be attracted towards number 1. I'm going to call that F12, the force of 1 on 2. Now, 1 is attracted to number 2 as well, right? But we don't care in this question because we're not trying to find the force on number 1. In the last question, we wanted to find the direction of the force on number 1. Here we want to find the force on number 2. Now, number 3 is there. Let's pretend 2 doesn't exist. 2 and 3 attract each other. Therefore, 2 is pulled towards number 3. I'm going to call that F32, the force of 3 on 2. You guys okay with the directions of those forces? It's always attractive, right? Okay, if you are attracted to the person next to you, then you will be pulled toward the person next to you. If 2 is attracted to number 3, then 2 is pulled toward number 3. It's attracted to number 1, it's pulled toward number 1. Now let's get both of these forces. The force of 3 on 2 ends up being a value of 1.31 times 10 to the negative 8 newtons. And F12 ends up being 1.25 times 10 to the negative 8 newtons as well. Make sure you can get both of those forces. Just straightforward gm1 m2 over r squared. But make sure that you can get those forces. When we do that, we then say F net is equal to the sum of the forces, F32 plus F12, and we add them up. But we have to be careful here. F32 is 1.31 times 10 to the negative 8 newtons, and F12 is negative 1.25 times 10 to the negative 8 newtons. That's why we drew that free body diagram, right? Is to get the negatives and the positives down. We add those together. We end up getting 5.6 times 10 to the negative 10. 5.6 times 10 to the negative 10 newtons. How many people get that one? Okay. You guys okay with those forces, the right directions and so on? Listen, I'll tell you right now, if you got to your unit assignment on Friday, okay, you saw that question number 6 was a question like this. I'm telling you right now, you're going to get a question in your unit test just like this. Okay, just like three masses in a row, find the net force on one of them. Okay, no tricks to it, no harder than this, no easier than this, just this level of difficulty. 3. The net force of gravity acting on object number 3. Here's object number 1, here's object number 2, here's object number 3. Let's pretend 2 doesn't exist. 2 is not there. Do 1 and 3 attract each other? Of course they do. 3 is therefore pulled towards number 1. We'll call that the force of 1 on 3. Now, 1 is also pulled towards number 3, right? But 2 words. Who cares? We don't care that, in this question, we don't care that 1 is pulled towards number 3, right? In question 1, we did. But in this one, we're trying to find the force of on number 3. Now let's put number 2 back where it was. 2 and 3, do they attract each other? Yes. That means 2 is pulled to the right. 2 is pulled towards number 3, right? But 2 words? Who cares? We don't want to find the force on number 2 in this question. That was for the last one. We want to find the force on number 3 here. 3 is pulled towards number 2. We're going to say the force of 2 acting on number 3 is to the left. It's pulled towards number 2. So we can find the values of both of these forces. F23 is equal to 1.31 times 10 to the negative 8 newtons. We've already found that in a previous question, right? F13 is 2.37 times 10 to the negative 9 newtons. We've also already found that one. Now we add them up. This one's a little bit easier to add up because they're both in the same direction. But they're both negative. Because they're both to the left. I think when I read the answers out to you guys, I said this was 2.4 times 10 to the negative 8 newtons. It should really be negative 2.4 times 10 to the negative 8 newtons, right? Because the net force is to the left on that. And finally here, let's have a look at question number 5, which is find the net force of gravity acting on object number 2. We do the same, we go through the same process here. We draw the free body diagram. Number 1 pulls on number 2. They attract each other, right? 2 is pulled towards number 1. We're going to say F12 is downward because 1 pulls 2 towards it. Now, 1 gets pulled upward towards number 2, right? But we don't care. Not in this question. Now, what about 3 and 2? They attract each other as well. Therefore, 2 is pulled towards number 3. 3 is pulled towards number 2, but that's for another question, not this one. Let's find the value of F12 and F32. F12 is G M1 M2 over R squared. The value for that one is F12. Here, let's label this better here. This is F12 right here. And this one is F32 right here. F12, it has a value of 1.11 times 10 to the negative 10 newtons. We find that by G times 50 times 30 over 30 squared. And then we say F32 is G times 50 times 40 over 40 squared. That gives me a value of 8.34 times 10 to the negative 11 newtons. We got to add these together, right? But we don't add them together the same way as we added them together in the last question. Yeah, Dexter? F12 is G times M1 times M2 over R squared. So this is my constant. M1 would be 30. M2 would be 50, right? 30, 50 over R would be 30 meters, and it would square that. Dexter, does that make sense? So we do the same thing for F32 there. And then once we get both of those, we got to add them up. But how do we add these guys up? Different than in the last question, right? 1.11 plus 8.34. Not quite as easy as that. This time we've got to draw a vector diagram. We've got F32 is 8.34 times 10 to the negative 11. And we're going to say F12 is this way. That's value is 1.11 times 10 to the negative 10 newtons. And the resultant vector, which is the net force here, we can find by the Pythagorean theorem. F works out to be here 1.4 times 10 to the negative 10. And theta we're going to say is the inverse tan function of opposite over adjacent. Theta works out to be 53 degrees. Quick mistake. Got to fix a quick mistake here, guys. Just brought to my attention. Question number 3. These numbers appear to be correct, but somehow I did the math wrong. When I add those together, I shouldn't get negative 2.4 times 10 to the negative 8 in question number 3. I should get negative 1.5 times 10 to the negative 8. 1.5 times negative 8 newtons. Is that right now?